I am doing problem number 21 on page 22. Gravity is the force that determines our weight. The gravity on Earth is approximately 9.8 meters per second squared, whereas the gravity on the Moon is approximately 1.6 meters per second squared. If someone weighs 180 pounds on Earth, how much will he weigh on the Moon in pounds? The first thing I want to tell you is that gravity is sometimes measured in newtons. So you maybe will see a different newtons per kilogram. Gravity will not always be meters per second squared. And I don't know why that came to my mind, but just for your information. Okay, the two things that we're comparing here, what are they? What are the two things that this problem compares? A lot of people tell me weight and weight. Well, does that really help me? Weight and weight, that doesn't tell me anything. But if I say my earth weight and my moon weight, that is a little more on the mark. What we're actually determining is gravity. We're determining earth gravity and moon gravity, and then we're comparing that to pounds. But I'm going to leave it as earth weight and moon weight because I think that's probably the easiest one to understand. But the first thing I have to realize is that the gravity on Earth is 9.8 meters per second squared. And the gravity on the Moon is 1.6 meters per second squared. Now here's the cool thing. Meters per second squared is the same in both of those, exactly the same, so we can just cancel it. We don't have to keep up with that. We can just reduce that down to the numbers involved. On Earth, Neil Armstrong would have weighed, I would say, about 180 pounds. So let's figure out what he weighed when he was on the Moon. Now, Neil Armstrong was the same man on the Earth and the Moon. He didn't change. His physical mass did not change. What changed is the force of gravity between the two locations. So if Neil Armstrong had stepped on the scales on Earth and he weighed 180 pounds, and then he brought those scales to the Moon and he stepped on the scales on the Moon, he would only have weighed 29.38 and then some, so about 29.4 pounds. Now think about that. If you got on a spaceship and you went to the Moon right now and you stood on scales, you would weigh significantly less than what you do on Earth. And that is entirely due to the force of gravity. Mass doesn't change. Neil Armstrong was the same man in both locations. We're talking about a few hours travel between two places. He didn't change. He didn't lose weight. He didn't change at all. His mass did not change, but his weight did because of gravity. And a rule of thumb, if you have to convert Moon and Earth weights, do Earth weight divided by 6, and that will give you the approximation of your Moon weight. So Earth weight divided by 6 is roughly your Moon weight. And this is C. Which is why Neil Armstrong needed a spacesuit to survive on the Moon, because of the differences in those conditions. Okay, number 22 is on page 23. It says to consider the map below. What is the actual distance in miles between Smithtown and Bullville? So we have to look at the map to get the scale. And the scale is 1 unit is equal to 15 miles. 1 unit is 15 miles. So we need to know how many units there are between those two towns. And there are roughly 2.5. It's a little bit hard to eyeball, but roughly 2.5 units. So I will do 15 times 2.5. And that is 37.5 miles. And that, of course, divided by 1 will not change. So it is 37.5 miles between the two towns. And we're looking at option D. Number 23 is one of my favorite kinds of problems. I've always enjoyed these. Jessica is 5.5 feet tall and casts an 8-foot shadow during the day. At the same time, a tree casts a 14-foot shadow. Assuming the ratio of height of an object to its shadow is proportional, what is the height of the tree rounded to the nearest thousandth of a foot? So I have to draw. I love to draw sketches. I'm not good at it, but I like to draw them. So here's our pretty tree out in the yard or wherever it is. And we have no idea how tall it is. That's a tough thing to determine. But over here is Jessica. And I do know her height. We can easily find Jessica's height. And somebody has already done that for us. So somebody's already said that Jessica is 5.5 feet tall. And then the sun comes out to help us. So we've got the sun up here, and that's going to cause a shadow to form on the ground. And assuming that we measure these at exactly the same time, this is going to help us find the height of the tree. The tree casts a 14-foot shadow, so we can stretch a tape to find that. Jessica is casting an 8-foot shadow, and we want to know the height of the tree. So you have your proportion. You have height over shadow. So we have height over 14 equals 5.5 over 8. So 14 times 5.5 is 77. And divide that by 8 is 9.625. And they told me to leave it as thousandths, so that's the answer. About 9.5 feet, roughly. 9.625 is B. Okay. Love those problems. Anytime you're looking for the height of a flagpole, the height of a tree, distance across a lake, those kinds of things you can do with this kind of math. Okay, I'm going to stop this video and I'll see you in the next one for problem 24.